Oke, saya mulai saja, Rik. Ini langsung oleh saya.
Ya, sudah on air, Pak.
Oke, baik. Okay, so we will start our lecture. So that thank you to Dr. Eldon Rene. So I think I would like to introduce Dr. Eldon. So he is now a senior lecturer in the IHE Delft Institute for Water Education in the Delft, the Netherlands. So he works a lot in the wastewater biological treatment and also for the waste gas treatment, and also working on the non-point source pollution prevention, resource recovery from the waste gases. And also he works also on the environmental process control and also in the eco-industrial park. And Dr. Eldon also currently serves as the managing director for the review in environmental science and biotechnology, and also in the Journal of Environmental Engineering. And there are also the editor for special issues, either in the bioresource technology and others. I think Dr. Eldon is quite active in the scientific publication. So today, Dr. Eldon will give a lecture on the role of different bioreactor configuration for the treatment and recovery of useful products from waste gases and wastewater. So the time is yours, Eldon. So
yes,
please.
Thank you, Professor Tjandra, for your very nice introduction, and also for inviting me to give this nice lecture with a lot of participants. And I'm really pleased to give this lecture to all of you. So I would like to start my presentation, but before I go into the topic, I would also like to give a little bit of an introduction to the institute where I'm working in the Netherlands. It's called the IHE Delft Institute for Water Education, and we are located 1 hour from Amsterdam in a city called Delft. And that is the same city where we also have the Technical University of Delft that is located also, which is close by. And the institute that we work, it doesn't have a bachelor program. It starts with a master program. We have PhD, and also we do focus on a lot of capacity building projects, which also Professor Tjandra has been actively involved with our research group here in the same department, together with Professor Damir, and also with Carlos, Hector, and many of the other colleagues from the department. So the institute focuses mainly on water issues. We focus with drinking water. We focus on sanitation. We also focus on resource recovery, because that has been also the prime focus for the last few years. It's not just treating water, but we also want to recover some of the useful products or byproducts from water or wastewater. But then from the mandate of the institute, you all know that there is a severe need for drinking water. Okay, there are countries which have enormous amount of water, but there are also countries that don't have sufficient amount of water. So there are water scarce region. There are also countries that have and risk from flooding and other type of natural disasters. So the institute was actually started in 1957, and so far we have trained more than 24 or 23,000 water professionals from over 190 countries. Okay, so it's an institute that focuses exclusively on water issues, and the mission of our institute is the institute works in partnership to strengthen the capacity in the water sector to achieve global sustainable development. So we all know about the sustainable development goals. So our institute also has identified a few of these SDGs, and we strive to work together to focus on achieving these SDGs. So this is done in 3 pillars. The first pillar we call the education and training. Education is nothing but the master degrees that we offer. At the same time, the institute is also has also customized the courses, not in the semester system. We have modules. Okay, modules means each module runs for 3 weeks. So the 3-week program also becomes a short course. So if you would like to come and join one of these programs, then you are also welcome. So we have a lot of short course participants who come from different countries. They come here, they gather specific skills that are required, and then they go back to their home country. Okay, so it's not that you have to follow the entire program. You can come and choose whichever courses that you want. And we also have a new program that is called a graduate diploma. It's called GPDP. It's a graduate diploma program where you can also customize and choose different courses, and then you get a graduate diploma. Okay, so we offer a very good flexibility between the different tracks. You can take a course that is from engineering aspect. You can also take courses from the management, governance, and different type of courses that can customize according to your requirements. Okay, so that is the first pillar, that is called education and training. And with respect to training, we also do a lot of tailor-made training programs. For example, if your university wants a certain expertise, or to develop a new program, or to develop new skills, then our staff members, together with also other experts from the field, we normally offer such kind of training activities. So the training can be in your home country, or you can also select 10 or 15 members, and they can also come here for a 1-month training, a 10-day training. So there are different modes in which we do this training. And the other thing is research and innovation. This is very common in, like, also in your university, we have PhD students and master students who also do research. And the third one is the institutional strengthening. So this is the prime focus also of our institute, where we work on different capacity building projects in the developing countries. Okay, so most of our partners are from Southeast Asia, then from the Latin American region, the MENA region, and also the African countries. Okay, so this is where we focus our institutional strengthening activities. So I'm not going much into the details. So this is what I had mentioned. We offer MSCs, short courses, online courses, and also tailor-made training. So if you have any desire to put forward a proposal for a tailor-made training or other things, you're very free to contact one of the staff from the project office, or you can also contact this email address. Okay. Okay, friends. So I'm very happy to give this small introduction, but now I would go into the topic. So before I go into the topic, I would like to tell what are the learning objectives of this lecture. Okay, so you're going to spend the next 1 hour or 1.5 hours with me. We will have some very nice discussion. Okay, it's not that I will be talking all the time. I also want you to share your experiences with everyone, so that we will also co-learn from each other. Okay, and if you don't understand something, or if I'm very fast, you please tell me to stop. Okay, or you can also put your questions on the chat box on the right side. Okay, I also see that submit question, please go to the link. So there is also a link where you can put your questions. Okay, that's also great. So the learning objectives are to realize the practical applications of different bioreactor configurations and their role in resource recovery. So all of you must have, or might have, at least a little background, okay, on bioreactors. Okay, we also had a very nice talk by our friends on Wednesday, where they also explained about different reactor technologies, different processes, and they also showed some very interesting results from their research. So in the same way, there are different types of batch reactors. Either it can be a batch reactor, a continuous reactor, it can be a fed batch, it can be semi-continuous, it can be operated in different modes, with a recycle, without recycle. It can be a single stage, a 2-stage, It can be 1-tier, 2-tier, it can be different stages of bioreactor. Either it can be a standalone process, it can be a hybrid process, it can have innovative packing material. So all these bioreactor configurations that are used for wastewater, they can also be customized and adapted for waste gas treatment. Okay. So I'm not going to talk more about wastewater because many of you know about the conventional wastewater treatment processes like the activated sludge, trickling filter, rotating biological contactor, membrane reactors. So in my presentation, I will focus more on waste gases. Okay, the waste gases are nothing but gases that have a lot of contaminants that are present in the gas phase. So this can be a volatile organic compound, like for example, benzene. It can be a volatile inorganic compound like hydrogen sulfide. It can also contain other components that are maybe in trace levels, or it can be also in high concentrations, but it depends on the process, the conditions, and the raw materials used by the company. Okay, so the first thing is I would like to specify in my presentation a few bioreactor configurations that we can use for waste gas treatment and also for resource recovery. And I will also tell you how to optimize bioreactor configurations. And if you have some issues with troubleshooting, you can also do troubleshooting, which I will also cover. And then at the end of this lecture, you will be also able to suggest some options for downstream recovery of the valuable products. Okay, so it's not just treatment alone. We also try to convert the gaseous form of pollutant into something that is useful. Okay, which means, for example, the volatile organic compound can be converted by certain microbe-mediated processes into valuable products. It can be a platform chemical, it can be biogas. Okay, so it can be anything that depends on the process. So in our chair group, the chair group is called Pollution Prevention and Resource Recovery Chair Group. We focus on all the three aspects of waste. We focus on solid waste. For example, we have a research line which focuses exclusively on recovering critical elements, precious metals, base metals from electronic waste. Then we also have a researcher who is focusing more on dry or wet anaerobic technologies. And we have another research group that is focusing on biochar, hydrochar production. Then we also have a group on solid waste management and on the application of eco technologies. For example, an algal photobioreactor or an algae bacteria consortium for wastewater treatment. And I'm focusing more on waste gas treatment. Okay, so that is my focus. So this is a very nice schematic that gives you the application of different environmental concepts and technologies and modeling tools for environmental sustainability. Okay, so when you look at this simple schematic, it's very clear that it's not just treatment. We also need a very good monitoring protocol if we really want to assess the sustainability of the processes or sustainability of the ecosystem. For anything, we finally need a very good monitoring tool. Once we have a monitoring tool, then we will be able to at least suggest options to control. We can do an online controller, for example. We can measure different parameters in bioreactors. We can also adapt technologies for water reuse. And now recently, as you all know, everything is connected with remote sensing data, GIS, and you can still make all these data that are available to environmental engineers in different conditions. Okay, and there are also a lot of new tools such as the application of artificial neural networks or artificial intelligence tools for prediction, for modeling, and also for controlling different state variables in a bioreactor. Okay, so when you have all this thing that is in place, it's quite easy to control the bioreactor or a bioprocess so that you can trigger or to model a system into the way that you want it to treat the pollutant. Okay, it's not just a pollutant is just absorbed or just removed. No, it's also, it is probably absorbed, biodegraded, or biomineralized into some useful products or to carbon dioxide and water if it's an aerobic process. Okay, so if you look at the whole concept of environmental sustainability, then of course the bioreactors or the bioprocesses, they also have a major role to play in water treatment, wastewater treatment, and also for resource recovery. Okay, friends, now before I go into the first slide, I have a few questions for all of you. Okay, you can use the chat. What are the different types of solid waste generated in your house, or if you're a student staying in a dormitory or a hostel? What are the solid waste that you generate? You can use the chat and you can type. Okay. What are the solid waste that you generate? If I ask you a very simple question, you can use the chat function and you can type. Yes. Okay, it can also be your office. Okay, because I'm also sitting in my office. I also have a plastic already. I have plastic. I have already a paper cup. Okay, very good. I see food waste, biodegradable and non-biodegradable. Yes. So can you be a bit specific to say what is biodegradable, what is non-biodegradable? Okay, very good. We go a little step further. Chemical waste, battery, bulb. Okay, but is the battery and bulb generated every day? That is my question now to you, to Patricia, Susanna. Do you generate batteries and bulb every day as a waste?
Okay, Patricia, you may open your mic. Please.
Yes, if you like, yeah. Okay. Okay, it's maybe once a year. Okay, so let us not consider that frequency, because I'm asking a frequency that is very common. Okay, every day. Let us consider every day basis or a weekly basis. Okay, so the answer is very clear that we have plastics, we have food items. Okay, so I think we are not wasting rice or meat or other foods, food as such. Probably these are some residues that are comes from the cooking or the peel of the skin or vegetable skin or other things. Okay, I think we will not waste food, isn't it? As such, a prepared food is not wasted. Okay, then we see plastic waste. Okay, friends, this is very important. The reason is, if you know the composition of the waste, the quantity of generation in a waste or a household, that is when you can decide what is the next step of treatment that you can adapt. Okay, if you say that, okay, in my street it is full of food waste every day. Okay, if it is food waste every day from every house, then I would go for a very nice technology that would convert a food waste into energy, right? You can also do anaerobic digestion. You can produce biogas. You can produce bioelectricity. You can also convert the food waste into other value products. You can convert them into fertilizer. So there are different ways in which we know. So if you say that my street is generating a lot of plastics, then plastics can be separated. You can then go for recycling plastics, or you can produce pyrolysis. You can do a lot of things with plastic. Okay, so the composition is really, really important, and you need a very good strategy to quantify how much it is generated. Is it generated every day, every week, or over a period of year? Is it generated every year? Okay, so this is very important for any of the treatment processes. You need a very good strategy to identify what are the concentration and composition of the waste stream. Okay, so we just took a small example of solid waste, but this is the same for wastewater. It's also the same for waste gas. Okay, so waste gas is also a form of air pollution. Okay, friends, now let me ask you another very nice question. Okay, we have already covered point number 2 and 3. Point number 4, can you type? Okay, can you type? What are the different type of bioreactor configurations that you have heard or that you know? Okay, what type of bioreactors do you know? Or you can write the name of the bioreactor configurations. Okay, very good, Christian. Submerged bioreactor, solid state bioreactor. Yes. So these are all for fermentation, if I'm right. Am I right, Christian? Submerged bioreactors. Yeah. Okay. Very good. And what about others? Can you please type some names that you know? Okay, very good. Say photobioreactors. Yes. So if it is a photobioreactor, we have algal biomass in it because there is photo light. Yes. Okay. More, please. Okay, I think I got all the answers now from Desi Leon. Am I right? Desi Leone. So we have a continuous stir tank reactor, bubble column reactor, airlift bioreactor, fluidized bed, packed bed, photobioreactor. Okay, we have all the type of reactor, which I am also going to cover. But now I would like to have a small discussion with these nice points. Okay, Desi Leone, okay, if I'm right with your name. Which type of reactor configuration will you choose for wastewater treatment? Okay, I mean for industrial wastewater treatment, among these reactor configurations, which one will you choose and why? Let's assume it's from a textile industry. Okay, it's from a textile industry. Like let's say a textile industry produces a lot of color containing wastewater. It has dyes. It has high COD. So which reactor will you choose from here?
I guess I'll go for the anaerobic membrane bioreactor, provided that it has the efficiency to actually degrade colors.
Okay, so you mean that all of this reactor that you have mentioned will not work for textile. Is that right?
Well, it may work. I guess it's the I think it's more of the bubble column or pack bed, I think. I'm not sure though.
Okay, so the bubble column, airlift, fluidized bed, they all work in a similar way, isn't it? Because the biomass is in suspension, but in a packed bed, they are attached. A photobioreactor is also a suspended growth process. A CSTR is also suspended growth. Am I right?
I suppose so.
Okay, so very good that you also mentioned about this anaerobic membrane bioreactor. Yes, it is also very good. For high strength COD containing wastewater, anaerobic processes are very good because they can work at very high organic loading rates. Okay, we call that as OLR. At very high organic loading rates, the anaerobic reactors, for example, a UASB reactor, a EGSB reactor, they are all able to work with very high performance, and they are able to convert them into biogas. Okay, or of course, or also many other reactor configuration, many other useful products. So now, we have seen quite a lot of reactor configurations, but please, friends, understand, okay, you have to now understand for wastewater, it's a little bit different. For waste gas, it's the criteria are different. Okay, the reason is the waste gas contains a lot of pollutants that could be hydrophobic in nature. Okay, for example, if you take a chemical that is called alpha pinene, okay, pinene is not hydrophilic. Hydrophilic examples are methanol, ethanol. In the gas phase, they are all very hydrophilic compounds, which means they are easily soluble in water. When they are easily soluble in water, you can use reactor configurations such as a bubble column, airlift, fluidized bed, or a photobioreactor or other things. Okay, but if it is a hydrophobic compound, it's always advisable to go for a packed bed system. Okay, yeah, it's a packed bed system, but at the same time, when you also want to do a technology selection for reactor configurations for waste gas treatment, the first thing you have to know is the concentration of the individual compounds, the composition of the pollutant, then the generation rate. Okay, how many meter cube of gas is generated per hour? Then you also need to know whether these are all hydrophobic, these are all hydrophilic. And when you know at least a rough estimate of how much amount of waste gas is going to be generated per day, and then you can decide what size of the reactor do you want, and with what packing material or what reactor configuration. Okay, so before you go for any technology selection matrix, you need to really understand what are the criteria for selecting bioreactors, what is the composition, and then you go for a proper selection of the technology. So the first case study that I am going to talk is hydrogen sulfide removal under anoxic conditions. Okay, this was done by one of my PhD students, and we did some research that was mainly focusing on the removal of hydrogen sulfide, which is a gas phase pollutant, from biogas. Okay, so as you all know, biogas is not completely methane all the time. It only contains 40 to 75 or maybe 60% of methane, while you have other impurities such as hydrogen sulfide. You can also have siloxane, you can have CO2 and all the other things. Okay, the problem when you have biogas with hydrogen sulfide is that hydrogen sulfide, as you know, it's a corrosive gas. It will immediately start to corrode your pipeline that you will use for transferring the biogas. Okay, so, and on the other hand, it will also reduce the calorific value of the fuel that you are going to produce. So you need to focus on technologies that can be removed, that can remove the hydrogen sulfide. So in this case, what we tried to do was we used a sulfide oxidation process under autotrophic denitrification conditions, and we used specific bacterial strain that can grow under anoxic conditions, that is called the NRSOB. It will use nitrate, okay, nitrate as electron acceptor, and all the sulfur, these inorganic reduced sulfur compounds as the electron donor, and convert sulfur into elemental sulfur or sulfate. Okay, and this microorganism is called the nitrate reducing sulfur oxidizing bacteria. This is what we tried to do. So in this case, we chose a bioreactor configuration that is called a biotrickling filter. You might have heard the word biotrickling filter, and it is the same. Okay, it's the same biotrickling filter, except that we have all these, we have the system that is completely closed. Okay, because we are dealing with the gas phase pollutant, we cannot keep anything open, so we have to close them. And now you may ask me the next question: how did you generate the waste gas? Okay, you might ask me now, how did you generate the waste gas? So let me tell you honestly the answer. The answer is we did not generate biogas as such, but in the laboratory, we simulated hydrogen sulfide production. Okay, so if you want to produce hydrogen sulfide in the lab, you have to mix sodium sulfide, okay, Na2S, and H2SO4 in a certain combination in a homogenizing tank and you have to bubble nitrogen. Okay, we bubbled nitrogen because our biotrickling filter was not aerobic. Okay, it was an anoxic biofilter, so we don't have oxygen in it. We bubbled nitrogen. Once hydrogen sulfide was produced and it was bubbled with nitrogen, get carried away and it goes to the biofilter. So this is the biofilter, and within the biofilter, you can see these little cubes. Okay, these cubes are nothing but packing material. We used polyurethane foam as a packing material because it has high surface area, it is highly porous, it can have all the biomass that can grow inside. Okay, so we pack this bioreactor very nicely, but not, don't press it. We just loosely pack. Reason is, as you all know, after some time, the biomass starts to grow and it will then occupy all the pores. Okay, and so we don't normally pack it very tight. We just loosely pack it. And as this is a biotrickling filter and the microorganism needs nitrate, okay, nitrate is not in the gas phase, nitrate is in the liquid phase. So we prepared a synthetic medium with nitrate containing wastewater, okay, because nitrate is also a pollutant, and we pumped it in a downflow mode. Okay, so the nitrate was fed in a downflow mode, hydrogen sulfide was fed in an upflow mode. So once you have the upflow and the downflow, it's very easy to have very good gas to liquid contact. Okay, and this type of operation is called the countercurrent operation. And this is really nice for biotrickling filters, especially when you have compounds, when you have pollutants that are also readily soluble in water. So this was the configuration that we did, but I'm just going to show only, I'm not going to show you many slides about results. I will just show one slide, okay, with the results, or two slides. And as you all know, in wastewater, we talk about carbon to nitrogen ratio, we talk about COD to sulfate ratio, we talk about different ratios in wastewater treatment, okay? But in the same way, for gas treatment, we have in this case, okay, in this case means because we have nitrogen here, we have sulfur here, therefore we had what is called a nitrogen to sulfur ratio. Okay, okay, friends, so these are some ratios that we can easily manipulate now. Manipulate means we change the conditions or the concentration here, we change the concentration here, then we will be able to achieve different patterns of different ratios. But I would also like to say that the calculations that you use for a waste gas is more or less same, okay, but we use a different factor that is called inlet loading rate. In wastewater, we use organic loading rate, okay. Here we use inlet loading rate, that is nothing but gram per cubic meter of air per hour. Elimination capacity is nothing but the amount of pollutant removed per meter cube, okay, per meter cube of bed volume per hour. So the inlet loading rate is also gram per cubic meter per hour. Elimination capacity is also gram per cubic meter per hour. So this gram, in this case, we don't have benzene or toluene, we have sulfur. So it is the gram of sulfur that is removed per meter cube of bed volume per hour. And removal efficiency, as you all know, that's the same. So we have different criteria, and what we did with different N/S ratios, we found that the removal efficiency, okay, the removal efficiency of hydrogen sulfide, it was not very high, okay, it was not up to 100% or 99% or 90%, it was only varying between say 60 to 70 in the best case. But of course, there are also bioreactor configurations that can go to very higher loadings and that can also remove much better than this reactor configuration. But you have to understand that this is not an aerobic process, and the idea was to remove biogas in the presence of nitrate. Okay, so it's two pollutants that are removed at the same time. But in the case of nitrate, we found that the removal efficiency was close to 80% or 60 to 80%. And what you also see from this reactor configuration is it's very difficult for us, in gas-phase systems to maintain a steady state. You may ask me now, why your data points are going up and down, right? This is a very obvious question, and this question also comes from the reviewers, of the paper. Where the reason for that is, as you know, we did not have a canister. Canister means a tank, a ready-made tank that we buy from the company, which has hydrogen sulfide that is pressurized at high pressure, but we made this in our lab. So the problem is, once you dose this Na2S and H2SO4, it depends on the evaporation rate. Okay, it depends on the temperature, it depends on the liquid level here, it depends on many other factors. So that is why, if you look our inlet load, these black lines, the black lines are not in a straight line. Okay, they are going up and down for the most part of the work. But at least this study was able to do much better. But in some studies, I will show you in the further slides, it was not that really easy to control the gas phase concentration. So what we did in this bioreactor, because it's a nitrate reducing sulfur oxidizing bacteria, we also took one strain of bacteria from a hot spring in Thailand, because as you know, the hot spring has rich sulfur, isn't it? So we took one of this Parococcus strain, and we also did what is called bioaugmentation. So bioaugmentation means you have your already present microorganism that is doing the job, but now we seed it with a new microorganism that, with the hope that it will really perform well. Okay, but I'm not going into the results of those studies. But what I want to tell you is, a biotrickling filter can be applied for wastewater and waste gas treatment. Okay, but the good thing about these bioreactor configuration is you can customize it in different forms. Now, if you look at this slide, here we have a fluidized bed, okay, like our friend who mentioned previously, fluidized bed, bubble column. Okay, so this is also a very similar. We have bubble column reactor or a fluidized bed reactor where we have a packing material that floats and agitates. We have the biomass that's growing on the top of that or around the packing material. And that is the first step, okay? And then the treated gas goes to the next step, probably. You can also then use a biofilter, you can use a biotrickling filter, you can use multi-stages of this bioreactor configurations in order to remove different compounds, okay? The advantage of having such bioreactor configuration in stages is, if you want to have only a bacteria here, you can have them. If you want to have only fungal colonies, here you can have them. If you want to maintain low pH, here you can have. Okay, so this is one advantage of gas-phase bioreactors, that you can design, customize, and operate reactor configurations depending on the land space. Okay, you may ask me now, is it very expensive? Of course, it is expensive, because you also, when you go for any bioreactor design, you should also consider several costs, isn't it? You have to consider the land cost, you have to consider the cost for excavating, for piping, for network. You need to do a complete study. It's just like building a house. Okay, it's not that you build the reactor, you come and fit there. You need to have the space ready, you need people to work, you need tubing, you need electricity, you need blower, you need so many things. So in fact, these configurations are quite nice and very appealing, and it will be nice that if you can also initiate these type of research, okay, which means it's not just one system, one performance, and one pollutant. The good thing would be to integrate different phases of pollutant, liquid, gas, and also integrate different type of bioreactor with different functions and different microbial ecology. Okay, so these are called as advanced biofilm bioreactors. Okay, friends, before I go to case number 2, I would like to ask, do you have any questions? Because I don't want to keep talking all the time. Is there any question in the case study number 1?
Arik, it might be, is there any?
Yeah, there's still no any questions, sir.
In the Slido, I think probably I will check this Slido. In the Slido, it might be they sent to the Slido.
Yeah, but no question in the slide.
Okay, if there are no questions, it means two things. It means either they understood everything or they don't care.
Yeah.
No, I'm joking. Yeah, yeah.
Yeah, thanks. But one question, Eldon, because the sulfur, the sulfur may convert it to sulfate, and
Yes.
then make the acidic condition, right, in the media. So that will be one of how to deal because the media will be become acidic inside. So that may inhibit the biological processes.
Yes, Professor. Yeah, you are right. You're absolutely right. But I'm unable to find my screen now. Yeah. So in this, can you see my screen now?
Yes.
Yeah. So in this slide, we have pH control, basically. Yeah. We have a pH controller here, in this tank, because if you look at this tank, you are right. Okay, we produce because the sulfur is the sulfide is converted into a sulfate, and a part of them you can see here we remove them. Okay, we don't keep them because it gets accumulated, and then you will have a lot of other issues. Then you are right. So we do this adjustment also here in this feed tank, and also we do pH adjustment here. But a part of them is usually taken out, and of course it becomes a sulfate-rich wastewater. And there are of course technologies you can use other technologies where you can also precipitate with metals to get metal sulfide precipitates.
Yeah.
Or you can also go for sulfur reduction, SRBs. Yeah. But yeah, in that case, in this study, we did not do that post-treatment.
Yes. Okay, then I think I can. There's in the Slido there is a question regarding how can we collect and measure inlet and outlet of the H2S gas. How do we collect the so probably the question is about how can we collect and measure inlet and outlet of the gas hydrogen sulfide gas.
Yes, Professor, can you now see the slide?
Yes.
If you look here, this is the hydrogen sulfide inlet. In the inlet, we have here a small sample collection port. It's nothing but a small port, the hole, and we can pass a handheld. Okay, it's a handheld hydrogen sulfide or biogas analyzer. That is what we used. And this biogas analyzer can go up to a concentration of 5,000 ppm of hydrogen sulfide. So we only plug a tube and we collect the sample in the device, and it immediately shows the reading. So there was one inlet port here for inlet concentration, and the treated gas here we have another port for outlet gas concentration. But at the same time, we also have ports here. You can see here one in this on the right side, 1, 2, 3, 4. These are called gas sampling ports. They are in the reactor with holes. We can remove them, and we can insert this tube, and we can measure the concentration of H2S in different levels of the biotrickling filter. The reason for that is then we will be able to know how much. If it is 100 here, maybe it is 80 here, it is 60 here, it is already 0 here. We know what we call as the concentration stratification. Okay, it's stratified between the height of the filter material. So in this way, we know which part of the biotrickling filter removes a lot of pollutant, which portion removes less. So in order to do that stratification profile, it's very important that we also measure this. So yeah, that is the answer, Professor.
Yes. Okay. There's still some question in here is it might be do you have any trouble, or it might be the question is, do you find any problem during the operation, and then how to troubleshoot or to overcome the problem?
Yes, Professor. Yeah, it's a very interesting practical question. Okay, and as you can see here, we operated only for 140 days, but that is the result I showed here. But in fact, the reactor was operated for around 300 days. So the first problem what we had was pH control. That was very clearly highlighted by Professor about sulfate. Okay, when we have excess amount of sulfate accumulation. But then, you know, these are lab scale reactors, and we wanted to operate it in anoxic conditions, which means that we were not expecting sulfur crystals. Okay, sulfur means, yeah, these sulfur yellow color crystals, but we also had some yellow color crystallization here. That is probably because there might be some oxygen intrusion into the reactor. So there was partly oxidation also, but in any case, this was not a completely oxidized or an aerobic reactor. But the main problem what we had, okay, which I have not mentioned to you, was the pressure drop increase, because as you know, this is a polyurethane foam. Polyurethane foam is nothing but like a cushion, you know, like a sponge. It's a sponge, and when you continuously pass water and when you continuously have microorganisms growing, the weight increases. When the weight increases, it gets compressed. It was not, for example, when we operated, it started here, but then after a few days, it was almost compressed and packed. When you have this packing, okay, when you have this kind of issues, the water that you pass from the top, it will not flow. Okay, it will start forming a pool, you know, like a small swimming pool in the top. That is not what we wanted. But in fact, yes, that happened twice. That is mainly because of excess biomass growth, then compression of the packing material, and also the pressure drop increase. So now I would like to answer the next question. How did you get rid of that? The easy and simplest way, okay, it's a most trouble-free way in the laboratory is, first you try to backwash. Backwash means you stop all this. It's called a maintenance step. It will require at least 1 day of operation. You just pass water, okay, water from the bottom to the top, the presence of nitrogen. Reason why we want nitrogen is we don't want aerobic conditions. So in the presence of nitrogen, you only backwash from the bottom to the top. Okay, that is one way of doing it. Even if you think the pressure drop did not decrease, then you can remove the lid. Okay, you have to remove. You remove a part of the packing material out, then you add new packing materials and you mix it. So that is one of the safest way as well. Okay, because sometimes also in the industrial cases, packing materials such as pall rings or other plastic or ceramic, it's mostly plastic rings, they could rupture, or they could break. So in those cases also, they periodically replace during the maintenance step.
Yeah. So the other question is, I put it from the slide. What is the concentration of the hydrogen sulfide in the inlet? Yes.
Yeah, it's a very nice, interesting question, because here, if you see, I mentioned to you, it is 0.5 to 2%. 0.5 to 2% means if you convert it into parts per million, okay, ppm, it is, you have to multiply by 10,000, which means it is 5,000 to 20,000. 20,000 ppm is not allowed in our laboratory to work because of safety. We are not even allowed to work more than, if I'm right, greater than 500 also, yeah, we are not allowed. So what we did was, most of the time in our lab, we operated it at less than 500 ppmv. In some cases, we went up to 2000 ppmv, but that was only for a short duration of time.
Yeah, I think the next question from Slido, I think you have answered this one. Yeah, the filter need maintenance, right? And then
Yes.
So there will be some saturated condition. So
Yeah.
is the elemental sulfur also will attach to the biomass? It's correct?
Yes. Yeah. There was, but in reality, we were not expecting that.
Yeah.
Mm.
Okay, I think so. All the question from the Slido.
Okay.
You may
Okay.
move on. Yeah.
I'm going to now stop, and now I'm going to restart with my small tutorial. Okay. Okay, Professor and friends, can you see my slide now? It's not a slide, it's a Excel file. Yes?
Yeah, Excel file. Yeah, yes, correct.
Okay. Okay, friends, now I'm going to tell you, because, I have shown you many values. It's very important for all of you to know, how do these numbers come from? Where do they come? What do they mean? It's not that you only see a graph and you know what is the performance. No, you need to know, how does it come? Where does it come from? And how to interpret any data. Okay, you have data, but what is the science behind that? Okay, so I took a very simple example of a pulp and paper mill located in Indonesia, produces several VOC. VOC means volatile organic carbon, okay, or volatile organic compound, among which alpha pinene. Okay, I took alpha pinene. It's C10H16. Okay, that is the formula of alpha pinene. So the first thing is, you already know that it is alpha pinene. Alpha pinene, you need to now go back and check what are its characteristics. Is it easily biodegradable? Is it toxic to the microorganism? Is it hydrophobic? Is it hydrophilic? Okay. Then the researchers had decided to test the feasibility of using a biofilter. Okay, so it's a biofilter now. The previous example was a biotrickling filter. So in a biofilter, there is no liquid phase that comes from the top. Okay, friends, there we used a synthetic packing material. A synthetic packing material was sponge. Here, it's a biofilter. It is packed with natural packing material such as compost. So compost is nothing but, as you all know, we also in our garden, we have compost. So it's the same compost, but of course, not as a powder. Okay, at least with some size, you can sieve the compost to a certain diameter, and then you can add it. And ceramic beads were added because, compost, if you put compost in a packed bed, after some time, it will also get clogged. So in order to give a good structured packing, we also added ceramic beads. The biofilter was operated at different gas flow rates. So this is where we talk about residence time. Okay, friends, you might have now thought, oh, Eldon did not tell anything about hydraulic retention time or solid retention time, which you already hear a lot in wastewater. Okay, but here we don't use the word hydraulic retention time. We use the word that is called empty bed residence time. Empty bed residence time means, so if you have this as the bed, if the bed is empty, okay, if the bed is empty, that is the volume of the biofilter. Okay, so in this case, the empty bed residence time is calculated by volume. Okay, the volume is 0.05 meter cube. So this is not a very big reactor. Okay, and the flow rate is given here at different Q. So volume by flow rate will give you empty bed residence time. Okay, friends, this is a very easy calculation. You take volume, you divide it by the flow rate, you get the empty bed residence time. In terms of seconds, it is 36 seconds. So in a wastewater treatment plant, you operate them at different HRTs, as you all know, maybe 24 hours, 2 days, HRT, 10 days, I don't know, okay? You can operate at different HRTs, but in this case here, it's a high rate system. We operate it at very low empty bed residence time. And you can see here, they even operated it at 2.4 seconds, okay? It's the time that you close your eyes and you open your eyes again, the gas passes from the inlet to the outlet, okay? So these are extremely high rate systems where the gas particles, they don't spend no longer than maximum of 2 minutes, okay? So now I have also mentioned here that the researchers have done the research for 450 days. 450 days means they are not going to take sample every day, day and night. Okay, you don't have to do that because it's a long-term study. You can take at different time intervals. So this is the time you can see here, days, and up to around 450, they have done all these samples. Okay, so like what our friend has asked before, the concentration was monitored at the inlet and the outlet. In gas phase compounds, okay, for gas phase pollutants, there are two ways in where you can represent the concentration. One is as ppm, V, parts per million in volume, and or in gram per cubic meter. Okay, friends, we don't use the unit milligram per liter here. It is gram of pollutant per meter cube of air. Okay, that is the meaning. So Ci is their inlet, this is the outlet. This is the flow rate, this is the empty bed residence time. So once you know the inlet concentration, you can find what is the inlet load, isn't it? It's very similar to the organic loading rate for wastewater treatment. And then once you know the outlet concentration, then inlet minus the outlet, okay, inlet minus the outlet divided by the volume and multiplied by the flow rate will give you the elimination capacity. Elimination capacity is nothing but the amount of pollutant that is removed per meter cube of bed volume per hour. And the removal efficiency, I think all of you know how to estimate. Okay, so this is how we did this simple calculations, and they did this experiment at different phases. Phases means for any bioreactor, as you know, if you have a bioreactor, you add the microorganism, you add the pollutant, it will not remove everything from the first day. Okay, it needs some time, what we also call as an adaptation time or a startup time or an acclimatizing phase. So during this phase, the microorganism will slowly get utilized, will start using the pollutant as its carbon and energy source. So in this case, it was alpha-pinene. Alpha-pinene was given as the carbon source. So it has taken around 28 or 30 days to remove the pollutant with 100% removal. Okay. Okay, friends, now you have to be very careful when you say 100% removal. My suggestion to you is please don't believe those numbers. Okay. The reason why is the reason I'm telling you don't believe these absolute numbers, because in any gas phase research, okay, gas phase pollutant, if I inject the sample now, okay, and you collect the sample and you inject, you and me will get different values. I can promise and I can assure you, both of us will not get the same same value. It's because of I don't know why. It's mainly because of a little bit of human error, then a little bit of sampling time, sampling volume, the level that is present. So it's always difficult to get a concordant value, but at least we will be able to get very similar values, okay, or we should be able to get similar values. The second thing is the sensitivity of the equipment. For example, this VOC, alpha-pinene, is measured using a gas chromatography, okay? If someone tells you that 100% was removed, you should immediately ask, what was the minimum detection limit of your equipment? You know, it's very important, because if they say that 100% was removed, but they still have emission, which the gas chromatography did not measure, then we are into trouble. You know, so it's very important that you also know what is the minimum detection limit of your equipment. So most of the time, GC, they are really very sensitive, and specifically gas chromatography fitted with capillary columns. Okay, they are, because now the whole analytical things have improved a lot. You can have a GC with the MS. So there are many new sophisticated technologies where analytical instruments where you can measure even now the microgram levels. Okay, so please be also, when there is a report that you read, please check what is the analytical things that they have done. It's very important to understand. Okay, friends, so this system of 450 days was operated with 7 phases of operation. And now I'm going to show you how the results look like. Okay, so normally this is how we plot. We plot the inlet concentration, then the outlet concentration. Okay, I think all of you can see this clearly. So you normally plot the inlet, the outlet, and you can also plot on the secondary y-axis, you can plot also the removal efficiency, okay, if you want to see that. So by looking at this kind of graphs, it's very clear that the outlet concentration depends on the inlet concentrations. Okay, it was not 100% removed at all. It depends on the values, but it is only at this point you can see that a lot of pollutant was almost removed. So now let us go to the removal efficiency, RE. You can see that the removal efficiency on day 1 was only 5%. Then it slowly increased, it became 100%. So that is when the acclimatizing phase, the startup phase is over. But then from different phases, the concentration changed up and down, okay? And the system never reached a steady state. If I look at these graphs, you know, even if a reviewer, if you submit this to a journal, the reviewer will first ask the question, where is a steady state? If it's a chemical engineer, they become more angry, you know, because for them, a steady state is a near steady state. It's not a pseudo steady state or a transient steady state or a transient state. But this profile, it looks very clearly as a study or a reactor which has not stabilized at all. Okay, so all these pseudo steady state, there is no steady state. It's more transient fluctuating conditions. There's only one point where we reached, we can say we got 100% removal. Okay, friends. So now this is not the exact way to draw. Then if you want to know much better, you plot the inlet loading rate, the elimination capacity as a function of the inlet loading rate. Okay, so now you can see that the points are completely scattered. The best way to interpret this figure is the elimination capacity. Okay, the elimination capacity increases with the increase in the inlet loading rate, but only up to a certain maximum. Okay, but then it starts to deviate, or it tends to stabilize or decrease. It never went to the top. But again, you can see one strange point here. Okay, this might be an error, or it could be an outlier. That's all. Okay, it's not a real measurement. But if you look at general profile here, you can see that the elimination capacity, it increases up to a certain value, then it's almost stable, or it really went down. So now, what do we get from this plot? Okay, from this plot, if you do elimination capacity versus inlet loading rate graph, you will be able to know what is the threshold of operating this biofilter. Okay, friends, and by looking at this figure, okay, at what loading rate would you operate the biofilter in order to be safe? Can you please look at this profile and type your answer? What loading rate would you operate the biofilter? But here you can see that they operate up to 6,000. Okay, but if you are an engineer, you want to take a decision, at what safe loading rate will you operate? Can you type? I'm looking for your answers. Okay.
Okay, maybe you can type in the
chat
box.
Yes, please type in the chat box. What loading rate will you apply? Okay, Kuntarini, 1,500. Okay, I'm taking your answer. Okay, let's see what others tell. 1,500 is almost here. Okay, friends, what about others? At what inlet loading rate will you operate?
Please type your just in the chat, bro. Any others?
Okay, so let us ask. Okay, I see a lot of answer now. 1,200.
1,200.
Okay. Okay, Yasdi, can you please tell to everyone why 1,200?
Yeah, for me, Yasdi or Watari, why you choose the 1,200? For Yasdi, why you choose 1,200?
Okay, very good. So at 1,200, there is a chance that you might get, because no, okay, it is not elimination capacity 100. Okay, it is the removal efficiency is 100.
Yeah.
Yeah, it's not elimination capacity. Elimination capacity has the unit of gram cubic meter hour. Okay, so the removal efficiency, it's I would not also use the word 100. It is always safe to say that it is greater than 90% removal. Okay, friends. So yes, the answer is right from Yasdi, and also I agree with the answer of Kundarini, because this is a system which is quite complicated. It has performed, but maybe 1,500, if you operate with 1,500, the maximum, and 1,200, we could say that 1,200 to 1,500 is the safe operating regime or region of the biofilter. Okay, friends. So these trials are very important if you want to go for a scale up. Okay, so this was a pilot scale system. It was operated for a pulp and paper industry, and they tested only with alpha pinene. Okay, now becomes the biggest complication. If you want to scale up and you want to put this biofilter in a real pulp and paper industry, the pulp and paper industry, it is not only containing alpha pinene, it also has other VOC mixtures like methanol. It has sulfur compounds. It has a complete cocktail of mix of pollutants. Okay, some pollutants may be very high, some pollutants may be less. So the removal efficiency will completely change when you have a mixture of pollutants. Okay. So in such a case, when you have a mixture of pollutants, when you have a mixture of microorganisms, you can very clearly see antagonistic and synergistic effects. Do you all know what is an antagonistic effect and synergistic effect? Can you open your microphone and you can tell to others what is the meaning of a synergistic effect? What is the meaning of an antagonistic effect?
Please.
Yes.
Reduce effect is the effect that resulted from the input that decrease the expected result. But the what is it? The other one?
And synergistic. Sorry.
Synergistic is the input will enhance or in line with the expected result that you wanted.
So when you say inlet, what do you mean inlet? Input?
Yeah, because in my understanding that we inject something into it, so that's the input.
Okay. Okay, very good. Okay, thank you so much. Okay, so I will rephrase a little bit your answer. So if the inlet concentration has two compounds, okay, for example, two pollutants. So the presence of one pollutant, okay, the presence of one compound will enhance the removal of another compound. That is called synergistic effect, okay, which means, for example, there is a very easily degradable pollutant. If it is present there and there is a non-degradable pollutant that is present there, one of the compound will have a antagonistic effect, okay, a negative effect on the other pollutants removal. So it is the same, okay, friends. This is very simple concept. It is applied in wastewater engineering. It is applied in solid waste management, also in waste gas. It's the same, okay. And also, for example, if you know the microorganisms, okay, we all do microbial community analysis. On day one, for example, on maybe on this slide, if I see here, okay, on day one, when we start the bioreactor, maybe we had only 5 different type of microorganisms. But on 200 day, maybe there were 50 type of microorganism, but there was 1 or 2, maybe the predominant, okay, or the dominant species that was present, and it was responsible for removing the pollutant. Okay, so please understand, in any biological system, it's very difficult, okay, biological system for waste waste treatment, wastewater or waste gas treatment, we don't essentially want a pure culture, okay. Of course, there are cases where we need pure culture, but in most of the biological waste gas treatment systems, we don't need a pure culture, as long as the treatment efficiency is high and we are able to meet the discharge regulations without any operational problems, okay, then we are quite happy with the reactor. We don't, although we prefer some reactors that can have one particular species of bacteria or a fungi, then it is nice, okay. So in some bioreactor configurations, which I will now show you after this, we have also tried a fungi, okay, a fungal biomass. The problem with the fungal biomass is the fungal biomass can tolerate low pH, which means it can go up to a pH of 4, 3.5, 4.5, then they easily grow, okay. And even when there is low humidity conditions, they can also grow. So when such situations are there, the fungal biomass will grow very faster than the bacteria, and it will outcompete the bacteria, leading to all the clogging issues. Okay, so you have to be also a bit careful when you select the microorganism, when you inoculate the microorganism. But in a realistic sense, okay, in a real full-scale system, they normally add activated sludge. You know, the activated sludge from a wastewater treatment plant, that is the best source of inoculum that has numerous bacteria that can be easily trained. Okay, trained means that you will acclimatize to remove the pollutant in gas phase. So most of the time it is activated sludge. Or if you take compost, for example, the garden compost also has its own type of microorganisms. Okay, so when you do this startup phase, the first 1 month of operation, during that time, that will be its own natural selection, that the microorganisms that like alpha pinene will start to grow, and those who don't like alpha pinene, they will say, okay, I'm not going to be here, I will not I will die, you know, so, or remain dormant. Okay, friends, do you have any questions on this graph and the explanation of the graph, interpretation of the graph? Yes.
In the Slido, there is a question,
Yeah.
regarding that the because of the gas concentration output is fluctuating. So that one, it might be difficult to meet the emission standard. So the four industry, as you may know, that they have to meet the standard. So that how we could
it's a very
to use
interesting
this
question.
technology.
Yes, Professor. Okay, but let me tell you, this is this data that I showed is it's not a real data. Okay, I only wanted to show this for the participants to understand that fluctuations are common, and I specifically wanted everyone to understand this part. Okay, the 100% performance line. But in a real sense, yeah, you are right that we never give concentrations as high as 10 gram per cubic meter or other things, because there are always limitations for biological systems, specifically biological waste gas treatment systems. They are operated at less than 5 gram per cubic meter. Okay, because you look here, I am showing you 10, 15. They are all extreme cases where you have deviations. So it's not operated at this. Usually it is less than 0.5. Okay, in a real sense, I mean in a real system, it's less than 0.5 gram per cubic meter. So in those cases, you will be able to very easily achieve greater than 95% removal efficiency. And even if you are not able to meet the discharge guidelines, in some industries, they have a post-treatment. Okay, post-treatment means the first step is a biofilter. The second step can be activated carbon. You know, our activated carbon is really a very nice finding for environmental engineering. It can absorb liquid phase pollutants, it can absorb gas phase pollutants, and we also use as a post-treatment step an adsorption tower. Okay, that is to make the regulatory board happy. Yeah.
The next question regarding the so that one is
it possible that mass transfer can occur 100% like the data on days 19 to 28? Is there no equilibrium between the liquid and the gas phase in the reactor? Okay, it's a very nice question. I did not go into the depth of mass transfer, but I have some very nice things to show you. Okay. Okay, friends, can you see my slide? Or
yeah, probably Arik, you have to turn off. Okay, please.
Professor, can you see my slide?
Not yet, not yet.
Ah, okay, because
okay, you have to start again. Probably you have to share again.
Yes, can you see now?
Yes.
Okay, this was a very nice question. Okay, it's a real mass transfer question. So now let me tell you, okay, this is, please don't look at those numbers. Okay, I only want you to look at the profile, how the trend, what you see. Okay, as I showed you before, when the elimination capacity, okay, is equal to the inlet loading rate. Okay, please listen to me very carefully. If the elimination capacity is equal to the inlet loading rate, for example, here, yeah, let me take here this point at 175. For example, here 175, you also have 175, which means 100% of the pollutant is removed. If you go here, for example, now 350, okay, but if you look 350 and you go here, the inlet loading rate is close to 550, okay, which means 100% pollutant is not removed. So now in this case, you can divide the region into two regimes based on mass transfer. Okay, so for example, up to here, I would say up to here. Okay, maybe from here, let's make a line at 300. So below 300 and above 300, there are two different regimes. On the left side, okay, this is the diffusion controlled regime. On the right side is the rate controlled regime. Diffusion control means it is mass transfer control. Whatever pollutant that you pass, it will penetrate into the biofilm. It is biodegraded completely by the microorganisms present in the biofilm. Or in other words, you can also, in terms of concentration, maybe the concentration was not sufficient enough so that whatever that you passed, everything diffused and it was all completely removed. Okay, removed means it's biodegraded. But on the other hand, rate limiting, okay, this beyond the 300, it's all limited by the rate. The concentration is quite high, but there are insufficient biomass that is present inside. Okay, so you can see here in one case, the concentration was not sufficient, but the other one, the concentrations become exceedingly high that the biomass was not able to remove completely all the pollutant. Okay, so that is where we have the mass transfer limitation. So if you want to go more into mass transfer limitation, first you need to know what is the diffusivity index, which comes from the mass transfer coefficient. You need to know what is the solubility of the compound in the water phase, the liquid phase, the biofilm phase, what is the thickness of the biofilm. Then you will be able to know what is the rate of diffusion of this pollutant into the biofilm phase. So biofilm phase is normally considered to be a water phase. Okay, we don't because biomass contains more than 90% of water. So it's basically the solubility of the pollutant in the water phase. So if you look at this figure, okay, please don't look at this figure, the other one, because that is I would call it a fake data or a dummy data. But this is a real data on the right this side. What you see, the left side is the diffusion limiting region, and the right side is the rate limiting region. Okay. Okay, is that clear, or is there any other question?
I think at the moment is no more questions regarding. Okay, you may continue. You still have the your presentation, Eldon?
Yes, Professor, I have.
Yes. Please.
Okay, are you able to see my slide? Moving?
Yes.
Okay. Okay, what I'm going to now show you, okay, because we have very limited time now, I'm going to show you the case study 3, which is very interesting. Okay, you might be astonished to look at this type of bioreactor configuration. So as I told you, you can imagine about different types of bioreactors. One of our friend in the class has mentioned so many different types. Okay, fluidized bed, bubble column, then fluidized bed, no, inverse fluidized bed, membrane, anaerobic membrane, aerobic membrane. In the same way, you know, because we were doing research, we also were interested in one very complicated bioreactor configuration called a monolith bioreactor. Okay, let me tell you, friends, if you go and search in the literature, maybe some people are working now on monolith, but at least from my knowledge, 10 years ago, nobody even worked on a monolith bioreactor. Okay, monoliths are normally used as in a motorbike or in a car exhaust to clean the air. Okay, to clean the combustion air, they use in the exhaust pipes of things, they use monolith. Monoliths are nothing but catalysts. They have catalytic converters for catching the pollutant. But in our case, what we did, we took this nice block. Okay, this is called a monolith block. They are nothing but, it can be made of cement. In our case, it was a ceramic monolith block. We took this monolith block, which has a lot of channels. You can see vertical channels. Okay, these channels, in our opinion, okay, we thought that for microorganisms to grow, it just needs a good support. Okay, and you will see that this is we also thought that it would provide a good support for microorganisms to grow. The same way, these days, you will also see a lot of researchers who are using what they call a hanging sponge reactor, loosely hanging sponge, which are also used as a media for the growth of microorganism. So we took this monolith block, it was a square block, we put that into a reactor, and we added a fungal species, okay, an exophialus microorganism, and we passed styrene. Styrene was the gas phase pollutant, and it was passed in an upflow mode, and water was also passed in an upflow mode. We wanted water because if you pass only air, and it will become completely dry, it's very difficult then for the biomass to grow. And that is why we had the fungal biomass growth, and we also had a nutrient medium. So it was a nutrient medium that had ammonia, it had nitrogen, phosphorus, potassium, all these as the main source of nutrients. And it was also passed from the top to the bottom. Gas was also passed from the top to the bottom. So in this case of operation, it was a counter current operation. Okay, the previous one, what I had mentioned, was a top and the bottom to up, which is a counter current. In this case, it is both gas and the liquid is from the bottom to the top. So we call this as a counter current operation. And the right side photo, you can see here, is from the top view of photo. You can see we were expecting that the biomass will grow only on the monolith, but we also found that it grew almost everywhere, because it's a fungal biomass. The fungi can grow even when there is little moisture content, and it can also grow as mat, like a mat. That is how it has grown here. And this is the bottom view. When we looked at the bottom view, it was completely different. The biomass did not grow equally in all the places. It was growing only in the center. Okay. So we did a lot of experiments, I would say, but it was not for 1 year. It was only a short-term experiment for around 100 days, but we had a lot of issues, which I will also tell you. After a short retention acclimatizing time of 20 or 22 days, we did the experiments under 2 different conditions. One is a residence time of 77 seconds, okay, and other one 19 seconds. And interestingly, you can see this is the removal in triangles. We were able to get 100% in many. 100% means 99% maybe, but here roughly between 80 to 90 at a residence time of 77 seconds. But now when we decrease to 19 seconds, okay, friends, 19 seconds is really a very short retention time. Okay, there is no contact between the microorganism and the substrate. So these are really high rate systems. We wanted to test the system's performance, but after some time, with greater than 90% removal, the performance really deteriorated. It went as low as 40%. But then, we also had a lot of trouble with respect to pressure drop. The pressure drop started to increase. It went up to 7. And on this day of operation, we had the same swimming pool effect. We had a complete clogging of the liquid in the top of the reactor because it was completely filled with water. Okay, so then we did again washing. Then again, we found that the pressure drop started to increase, but after that we really stopped the reactor's operation because we expected that it will still continue in the same way. Okay, but of course there are now a lot of strategies where you can also avoid excess biomass growth. But as I had mentioned to you, these systems are not applied at the real scale. We have only done it at the experimental scale, but sure, there are a lot of opportunities like what I had mentioned to you to integrate different bioreactor configurations, like what I'm now showing here. You can have a bio-trickling filter. You can also have a biofilter, okay, as a second stage. Or you can have a bio-trickling filter. You can have a monolith reactor. Third stage, you can also have an activated carbon system if it is not removed completely. Okay, so in general, what I would like to say, considering the time, is the first thing is very important is you need to identify what is the concentration composition of the waste gas. Then once you know that, you go for the next step to select the correct biocatalyst. Biocatalyst means a mixed culture of bacteria or a fungi, or you want only a fungi, or you want a bacteria that can tolerate low pH, because some of the industrial emissions, they are acidic in nature. So in such cases, you have to select different types of biocatalyst. If it has sulfur compounds, you have to utilize microorganisms that really likes the sulfur, okay, and it can convert them into different compounds. So all these systems can be very nicely engineered. They can be like what professor has mentioned, sulfur can also be recovered, okay. If you can engineer the process in a different way, you can also recover elemental sulfur. And now I was mentioning to you about these waste gases that have a lot of carbon. If you go for an anaerobic step now, you will be able to recover volatile fatty acids, okay. And you can change the pathway, you can change the microorganisms, you can have a lot of different types of enzymatic reactions within the bioreactor. So what I would like to conclude with this short lecture is, yes, it's a very nice idea to test, before you go to the pilot scale. At least at the lab scale, you should be able to test different bioreactor configurations. Then you go to the pilot scale. When you go to the pilot scale, it's important that you try something in a real environment, to put the pilot scale in a real industry, so that at least a part of their waste gas can be treated. Once you have something that is demonstrated at the pilot scale, then you go to a semi-industrial scale and then to the full scale. Okay. Okay, friends, is there any questions?
Yeah, things of it might be if you have a question, so just a short question, you may open your mic because we have run out of time, our time. So if you have any question or comment, please do so. Because now we already on our time is already 4 p.m. So
you can also ask me other questions. Okay, you don't have to necessarily ask the bioreactor. You can also ask other questions about my institute or other things is also fine.
Yeah, it is, but I think there's a question in the Slido, but it is in Bahasa Indonesia, but I will try to just to translate. So that you mentioned about the styrene, a gas styrene in the gas phase, right? So yes. You use water, or is there any other chemical liquid to use to absorb the styrene?
No, the styrene. So normally what we do, styrene is a liquid. Okay, pure styrene is a liquid.
Okay,
it is a liquid. So we take styrene into a nice bottle, a glass bottle, and we bubble air. So when we bubble air at a different flow rate, we have like an impinger. Impinger. It has one tube inside, one out. So we bubble it inside with air, and the gas comes out. The liquid does not come out. We only take the air out, and the air is passed into the monolith bioreactor. But there was another vessel, okay, that was for liquid. The liquid is not styrene liquid. That is a nutrient medium for the fungal biomass to grow. Because as you know, if we don't pass water, immediately it will dry. With high flow rates, it has air, so the whole bed will dry. Biomass will not grow. So we need at least a little bit of for biofilm to grow. We need moisture.
Okay. So basically, it is water, and then we include the nutrients media in the water. So this, what is the optimum pH in the bioreactor?
the optimum pH for it depends on the different system. Okay, if it is a system with activated sludge, bacteria, mixed culture system, the pH is normally in the range of 6.7 to 6.7 to 7.2. If it is a fungal biomass containing system, the pH optimum depends on the fungal biomass. So normally it can go up to 4.5 to 6.5. It's in the low pH range.
Yeah, things are probably I do not see my student because has been, you know, that the Dutch also marketing the shell packs
System.
system. So that I think there are a number of systems, but one of the system not far from Bandung using for to reduce the sulfur from the biogas treating the pulp from the pulp industries. So what is the key to run, because it seemed to be that the industry not really work, the system is not work very well. So that what is the key to run the pack shell system?
Okay.
I don't know how to pronounce it. Package.
The pack. Yes. But I don't know their technology and what they are using. But was that a moving bed bioreactor? What technology do they use?
The technology is not moving bed, but that one is just like just a column, like a bubble column system.
And they have these little balls, if I'm right, big balls as packing material. Ceramic balls.
I'm not quite sure
somewhere, but I'm not sure, because with these companies, they have their own what is it called, patented biofilm. Patented biomass, patented packing materials. So we don't know the real technology unless it is published, openly.
Okay.
So we are not involved with them. But my professor, Professor Pete Lenz, he has worked with them. I think you know from Wageningen University.
Yes. Probably, Elvina, do you have any question? You open your camera, Elvina?
Yes, I see Kundarini here.
Please, if you like to ask directly.
I just said hello to Eldon. Thank you for everything when we were in IG.
Yeah, I think so. Kundarini is graduated from IG, right?
Yes. With Peter van der Steen. Am I right?
Yes, that's correct.
Yes.
Great.
Please say hello to him too.
Yes, sure. I will too. I will tell, because we are teaching now a module 10 on eco technologies. We are together.
Oh, I see. Good.
Okay. So also good luck to all of you, and thank you so much, Professor, for inviting me. If there are any questions, you can also send me an email